Okay, so let's draw a picture. And some of you may be able to tell what I'm drawing. I'm not an artist. So, I don't know, perhaps you can tell that's supposed to be a spring scale, like a luggage scale or a fish scale, something like that. Perhaps you've used one of those, and inside there's a piece of metal, um, and it's a metal spring, and it is wound up usually, and it stretches out. And the reason that this works is because most metals have a very simple relationship between force and displacement. I could draw the same concept as you have in the spring, and I could illustrate, as many people do in high school physics. They take a spring, and I've drawn in just a block of material, and it's loaded with a force. And what you do is you measure the length of that spring or that piece of material as you apply different loads to it. And if you did that, you'd find that most materials have a straight line relationship. That is, it's linear. There's a linear relationship between force and displacement. If you measured the slope, and we often use the letter K for that, you find that was the slope. So it goes through the origin as a form of the equation that you could fit to that is the equation for a straight line, which is y equals mx plus b. It's a common way that it's written. Of course, it's just force, in this case, equals k, the slope or the proportionality constant, times x, the distance, the length of the material. And that's actually a kind of a handy equation, and it's got a name. It's commonly attributed to it. It's called Hooke's law. Perhaps you've heard of that. And it's just a straight line relationship between force and displacement. The problem with that is if you were to say take two materials now, or two samples rather of the same material. Okay, so I could take sample A, okay, of aluminum. Say it's 6061 T6 aluminum, exactly the same alloy, and then I take another sample of exactly that same material. Okay, and we'll call this one B though. But as I said, let's say they're the same material. Okay, same material. That's important. Same material, and I load both of those up with force, and I then take that and I plot now force versus distance for those two samples, A and B. I'd find that A had a higher slope and had a higher constant of proportionality, or sometimes that K is called the spring constant. And A would have an apparently higher spring constant than B would, and in fact B would fail. It would break at a lower value of force. And the reason that's a bit confusing is because it should be the same material. And so really, as engineers, we'd like to have a material property that we could use that would be independent of sample size. And so the solution to that is actually just to divide by the cross-sectional area. So let me show you what we do. So here's another sample again. We're going to pull axially, uniaxially, straight up and down, and there's the force. And this is the cross-sectional area. Actually, you know what? I apologize. I'm going to actually just change this figure up just a little. So there we go. All that stuff's gone. So I'm going to draw in this area again without the force, because what I want to do is I want to call that area, I want to call that the initial area, cross-sectional area actually. Oh man, I'm all over the place here today. Cross-sectional area. Okay, and then what happens when you apply a load to this, and that's what I'm going to draw with the yellow, is it elongates. And there's this new area, which we'll consider later. Okay, So this is, I'm exaggerating, hopefully obviously, the amount by which this is extending and getting narrower. But this is longer now and narrower. Narrower, okay? But what we're concerned with at this point is this initial cross-sectional area before we had a load on it. If we take that and use that, put that in the denominator below the force, we can define this thing called the stress. Okay, so this is the stress, and that's the Greek letter sigma. Okay, to put the equations into little red boxes just so you can identify that they're in fact an important equation, and that is, again, A naught is the initial cross-sectional area. Now actually I'm not completely thorough here because this, although we often just say stress, technically this is in fact the engineering stress. Okay, and that will become obvious a little or important a little bit later when we want to in fact account for this reduction in cross-sectional area that you see there. That will be accounted for with something called the true stress. But for now, the engineering stress is actually very, very useful. It's very commonly used, and it's just the force over the initial cross-sectional area. Similarly, we can define the engineering strain, the Greek letter epsilon, as the change in length over the initial length. Okay, so this would be the initial length. And then there's this little elongation here at the bottom and this elongation at the top. Now, because it has translational equilibrium, it's not moving. We've got half of the elongation at the top and half of the elongation at the bottom. If I fixed it on the surface, it would all be on one side. But just to define what that change in length is, there you go. That we put into our equation, and that defines our engineering strain, delta L over L naught. And so the nice thing about this is at the end of that, if we plot now stress versus strain, we find that for both A and B, that is these two different size samples we had up here, the curve is the same. It's independent of sample size. So now that we see that the two curves are independent of sample size, and they're the same, we can actually plot that Hooke's law again. Okay, so remember we had Hooke's law involving force and displacement as F equals Kx, right? So now if we plot stress versus strain, and you'll notice, I apologize, I didn't actually introduce this property, but down here on the x-axis, I plotted strain, where I would formerly have plotted force and displacement. So displacement here, displacement x is replaced with strain, right? Just as we said, force was not really sufficient because force depended on the size of the sample, and we normalized by cross-sectional area to get strain. Well, length isn't enough. This length is insufficient. It depends on sample size. So what we do is we normalize by the length of the sample. So we take that change in length, the little bit extra length that we get if we're stretching it out, divide by the total length over which that elongation is occurring, and that gives us this quantity which we call strain, or the engineering strain specifically. So now I've plotted engineering stress versus engineering strain, and we see that that at least the initial portion of the stress strain curve for most materials is straight, and regardless of the size of the sample, the curve is the same. And in fact, the slope here, where we saw previously the slope of f equals k, the straight line f equals k, kx, had a slope of k. Now, the slope of the stress versus strain curve here, the linear portion, is the modulus. And so we can rewrite Hooke's law as stress equals this constant of proportionality, which is actually called the sorry, correction, this one, new terminology. I like to use yellow for. So that's the Young's modulus. Okay, that's the proportion, the constant of proportionality between stress and strain. And we can write Hooke's law as stress equals Young's modulus times strain. And I like to also put, as you know, equations in a little red box. So that's an important one. And that is, as I said, that is Hooke's law.